Meta-level science, example 2, laws and energy. Meta-level science videos 1 and 2 review. Science is the mapping of mind, model, data, reality with methodological and continual improvements. At the meta level, a space of model needs to be created, with each model being evaluated in a number of ways. To avoid spaghetti and microscience, refactoring needs to be done. The concept of law in science is oxymoronic, as all models are gross approximations of reality. The second law of thermodynamics is only applicable to the study of heat capacity. The concepts of information structure and order are broader and evolving far beyond the concept of entropy. In this video, we will return other physics laws to their rightful place of models with specific properties. In this video, we cover 1. Energy conservation versus energy transfer. 2. What is energy and what is energy conservation? 3. The context of mechanics conservation laws. And number 4, mechanics laws as properties of dynamics models. Energy conservation versus energy transfer. Real energy. Almost every form of real energy is a transfer from one form of energy to another. For example, heat energy into electrical energy, solar energy into electrical energy, water hydro energy into electrical energy, wind energy into electrical energy, molecular energy into heat energy, and atomic energy into heat energy. Environmental energy and energy chaining. Most energy uses are based on either the environment, for example, solar, hydro, geothermal, or wind, or inner structure, for example, molecular or nuclear. Chaining of energy transfers is usually part of inner structure energy, where energy from one transfer is used to kickstart other energy transfers. For example, where the energy of one molecule being broken provides energy for other molecule breaks, e.g., burning gas or wood. All real energy sources are perpetual. Water, wind, and solar flows are continual. Fires will burn continually. Conservation in all of these reactions only indicates that the amount of energy stored will be transferred to other forms. The transfer is perpetual. The perpetual motion prohibition is a misuse of the conservation principle. It doesn't fit in normal, real energy sources. Setup, maintenance, and fuel supply are not part of energy creation or conservation. They are part of manufacturing and business. Setup energy. Energy used in digging a canal or building and maintaining a dam are not part of energy conservation. Fuel supply. Even with an engine burning fuel, energy conservation has nothing to do with gas, air, electric charge flowing in. Conservation is in molecule to fire energy flow. Molecule to heat is like a bowstring being released. Bows are not being pulled back, just more bows are sent in. Bow release is conserved. What is energy and what is energy conservation? The energy model and energy intermodel. Within some models, energy is a macro property, Macro property means a combination of sub-behaviors. It is a quantification of the motion of objects, including large numbers of interacting objects, where objects include mass and potential properties. Conservation in this context is a computational property. Energy is also a meta-computation property. Meta-computation means that it is a property that crosses numerous different models. It is the computational glue that connects the models. For example, between the macro-micro domains and the atomic domain, and we'll get to that in a moment, those domains. Conservation in this context is the computational glue. Meta-level science evaluates computational systems and differs from meta-computation, as defined above. Mechanics conservation laws and context. Textbook critique of conservation models. In Mechanics, 3rd edition by Keith Simon, there is a discussion on the conservation models associated with mechanics. And it's broken into 4 different domains: the celestial domain, the macro-microscopic domain, which is basically mostly the world that we live in, the atomic domain, and the subparticle domain. There's a discussion of, in general, how these conservation models hold within each of these domains. There are specifics in regards to linear momentum, angular momentum, and energy conservation. In general, conservation models hold in the celestial domain from a Newtonian mechanics perspective, with medium and space deviations for Mercury. At the macro-microscopic level, the complexity of interactions affects computability. At the atomic level, quantum and probabilistic models are needed. At the subparticle level, things become too complex to be clearly modeled. At the more specific level, for linear momentum at the celestial context, linear momentum holds, mechanical and gravitational, but requires composite bodies to be treated as particles. At the macro-microscopic level, linear momentum holds, mechanical and gravitational, but also requires composite bodies treated as particles. For linear momentum at the atomic level, there are issues at high velocities and accelerations. Charges in motion use momentum redefinition. At the subparticle level, again, it is too complex to be clearly modeled. For angular momentum at the celestial level, it holds. It requires the body seen as a system of smaller particles with their own rotations. At the macro-microscopic level, for angular momentum, also holds, but requires the body seen as a system of smaller particles with their own rotations. At the atomic level, for angular momentum, requires a body seen as a system of smaller particles with their own rotations, as well as a quantum model. So there's a bit of a change there when you have to go to a quantum view. Again, at the subparticle level, it's too complex to be clearly modeled, angular momentum. For energy conservation, it holds at the celestial level. Tidal and other effects need to be included. At the macro and microscopic level for energy conservation, it holds, but requires friction, and a heat inclusion. At the atomic level, energy conservation requires heat to equal kinetic plus potential of random motion of particles. Electromagnetic energy associates with the electromagnetic field. Again, at the subparticle level for energy conservation, it's too complex to be clearly modeled. Observations of critique. Computation models become more complex as scale gets smaller. This means that the computability and the tractability of the models become issues. For example, probabilistic and statistical models are used to handle some of the complexity because things cannot be computed out to the X level. They have to be probabilistically averaged out. Other observations include the requirement of the inclusion of multiple interacting forces. The models change or become composed of different elements as we start moving to the atomic and subparticle level. Other requirements include systems of particle models, which are basically macro properties. The analysis or critique is generous in statements of conservation, as quantum and wave behavior redefine motion at the atomic and subparticle levels. Handling subparticle complexity. There are many new computational tools that can potentially handle the complexity of subparticle behavior, including finite element analysis, computational fluid dynamics, fractals, artificial life, artificial intelligence techniques, neural networks, cellular automaton, genetic algorithms, reaction diffusion, on and on. To maintain consistency across the different models, you'd want to model energy as macro motion behavior of the subparticles in order to be in line with the same type of interpretation at the celestial and macro and micro levels. To maintain consistency across models, some form of environment energy flow or chained inner structure energy should be part of the subparticle model. The subparticle model should handle unmodeled perpetual energy sources, just as energy is handled in the same way at the micro level. And examples of what to model would be behavior seen in cold fusion, HHO, and magnetic generator interactions. Mechanics laws as properties of dynamics models. Laws of motion are properties of models. Computational dynamic system properties, or laws of motion, are applicable to a large family of models. Every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it, is one of the properties. Another property is the relationship between an object's mass, acceleration, and the applied force is the force is equal to the mass times the acceleration, where acceleration and force are vectors. And the third property would be for every action there is an equal and opposite reaction. Motion properties don't stand alone. Stickiness occurs. This includes Cushing behavior, intermodal energy transfer, and structure creation as objects collide or as they are attracted to each other. All basic properties should be on par with each other, e.g. motion, stickiness, structure creation, energy transfer, cushion, should all be on par. There are no laws in science, only properties, models, data, and other analytical features. Lessons learned. No model is reality. Energy transfer, environmental energy, energy chaining, and perpetual energy are all significant when doing energy business and manufacturing. Energy conservation is a computational and intermodal property. The broader set of mechanics laws are a combination of computational and intermodal properties that can be applied to a broad family of models. Current intermodels have inconsistency in conservation representation. New computational tools provide opportunities for subparticle modeling and introduction of consistency across intermodels. There are other important properties of mechanics systems, such as stickiness.